go. Cool. All right, so this, oh, there we go. All right, so where we are currently is, in compiling C control structures. And I think with this class, we started talking about that already, even though I may not have finished the entire module. So I'm hoping that you guys had a chance to kind of read that module and be able to understand some of the concepts. So this is the module that I'm referring to. It basically turns you into a compiler for the most part. Okay, it doesn't explain some of the other things that you also need to know to become a compiler, but it does help a whole lot. So the first part, I think we talked about this part already, which is section 3. So section 3 is talking about how to flatten control structures. And I don't really deal with a whole lot of, C does not really give you a whole lot of control structures, unlike some scripting languages where there are interesting ways to implement control structures. But C is pretty simple, okay? We have conditional statements. So what you see, the first chunk of code is the structured conditional statement. And what it translates to is, a basically flattened version of the same code. So functionally, the two chunks of code should be identical, but they are expressed differently. So the logic is expressed here using very clean structured programming, style. And over here, functionally, this code is identical to the code that is above, but it does not have structure anymore. Now, when I say it has no structure anymore, it means you do not need curly braces anymore. Okay, the curly braces, there's no need of curly braces. Even if block 1 consists of 6 or 7 statements and block 2 consists of 6 or 7 statements, in the original code, the curly braces are mandatory. But in the translated code, there's no need for curly braces, even if block 1 is 6 different statements. Does that make sense? Does everybody understand why curly braces are no longer needed after the translation? We good? Okay. Now this does go back to the syntax of C and C++, okay, which is something I did not go over last time, so I'll go ahead and mention that here. So in C and C++, when you have a conditional statement, so I'll just give you an example instead of giving you the abstract description. Okay, so if this is the actual code, okay, and then we have something after this, okay, so let's say we have a while loop after this, okay, which has nothing to do with the if statement, okay. Okay, so we have some code like this. I don't think anyone is going to have a problem of associating x equals y to be the then statement of this conditional statement. Are we good? Okay. So the question is, what if we have something like this? So now, syntactically speaking, or I shouldn't say syntactically, but by using indentation, it would appear I guess I plus 1 is also a part of the then statement. But in reality, it is not. Because in C and C++, the compiler expects exactly one statement after the condition of the if. In other words, okay, let me go back and use the mouse pointer. So what I mean is, as when the compiler parses this particular close parenthesis, which concludes the condition of the conditional statement, it is now looking for a single statement as the then statement. So what does it find? Well, it finds this statement here, to be an expression statement, okay? And it says, okay, I have found my then statement. And then what is it going to do? By the time it parses the I, it says, I might expect an else here. I might expect an else branch that starts with a keyword of else. This is not else. I'm done. This conditional statement is done at this point. So that means I guess I plus 1 is not a part of the conditional statement. It is actually after the conditional statement. Is that okay? So this is one thing that is really confusing, and I don't know whether in your cisp360 class, whether this was mentioned or not. Was it mentioned?
It was mentioned in my CISP 400 with blocks.
Okay, but not in 360.
No.
Okay, so that's why I kind of want to mention this because this is something that people do not remember. Because if there's one little thing you want to do, yeah, you don't need the curly braces. But if there are two things you want to do as the then branch, you need to use a block statement to contain those two. Yes.
It was shown that I was just told it was wrong. It wasn't explained
Ah,
that it was wrong.
okay.
Just don't go see Chapman at CRC. He'll just tell you it's wrong. It won't explain why.
I try to explain too much sometimes because I do look at things from the eyes of a compiler because that's kind of what I did before I became a professor here. So I maintain compilers, and and it has always been an interest of mine.
Are we recording?
Yes, we are.
Okay.
Yep, we are recording. Not, but your statement was not recorded. You're safe. If anyone questions that, I'll say I said that. Deal with it, right? Okay, so now we have an else here, okay? So if you have an else, then everything is good again. Because I gets I plus 1 becomes the else statement. Because the else is a key word to indicate that, no, we are not done yet, okay? We just specified the then statement, but there's an else part to it too. So in this case, okay, the way it is right now, I gets I plus 1 is the else statement, which means if x is not less than y, then we increment the value of I. Are we good so far? Okay, I can close the door. Oh, thank you. All right, so next. So we'll add some more stuff to this, okay? So let's say that we want to increment j in this case, okay? So I want j gets j plus 1 to be in the then branch, and in terms of indentation, it looks good, okay? But in this case, it's a compile time error. It's a syntax error. Because from the perspective of the compiler, this is how it's going to do things. At the end of this parenthesis, okay, after this parenthesis, it's going to say, I'm expecting one statement. It sees x equals y, and as soon as it hits the semicolon, it turns the expression into a statement. Okay, so x equals y by itself is considered to be an expression, but once it sees the semicolon, it turns into a statement. Is that okay? So after this statement, the compiler says, what should I expect after this? I can expect one of three things. One is the end of the current block. It can be the end of a function, can be the end of a local curly brace block. That's one thing that can terminate this whole thing. I can expect a statement, which has nothing to do with conditional statement. It is just the next statement. Or I can expect else, which is saying that, wait, this statement is not done. We have just parsed the then statement, but wait, there's an else statement after this. So those are the three options from the perspective of the compiler of what can happen. So the compiler says, oh, it's j blah, 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 okay? It is not else. So that means at the time when the compiler parses this j, it would already have known that the conditional statement has terminated. We are done with the conditional statement. It won't give you a syntax error at this point because it's perfectly okay to have an assignment statement after a conditional statement. Those two are independent. They have nothing to do with each other. Syntactically, we are good. Okay? So it would parse this and say, okay, I see j gets j plus 1 is an expression, but since we have a semicolon here, that turns it into a statement as well. Okay? So we have a statement that is outside of the conditional statement, and that's not a problem. Then it sees else, and it goes like, I don't know who is supposed to process this else because we are not in a conditional statement. And that is when the compiler will complain and say that this else has no if corresponding to it. So are we doing okay so far with this kind of analysis? Okay, I know this is not a programming language class, but I think it is important for you guys to understand how what is the syntax of C or any C-like language when it comes to conditional statement. Because this is also true for Java. It's also true for JavaScript. It's also true for PHP. It's also true for Perl. So any programming language that is quote unquote derived from C and C++ would interpret conditional statements exactly the same way as what I just said. Are we okay with this? Okay, all right. So getting back to here, okay, now we can kind of understand why, if block 1 has like 6 different statements, in the original code, it is necessary to have the curly braces because otherwise, the syntax just won't work. But after the translation, I can have any number of statements here, including 0, and it will still be okay. Is that okay? All right. So the other one is a conditional statement that has no else in it. That one is a little bit simpler, okay? You can kind of look at this one as the one that has an else, but block 2 itself is empty. So if block 2 is empty in this case, then this particular block here is also empty, okay? Which is okay. It's just, you're using some extra code to do something that is not necessary. In other words, this go to L2, which was the intention of go to L2 here is to jump around the else block so that we can get to the end of the conditional statement. If you don't have an else block, okay, if block 2 is empty, this is still okay. It is not incorrect. It is just not efficient. You have a jump instruction that doesn't have to be there. So is that okay? So you can always look at a simplified conditional statement that has no else branch as something that has an else branch, but the else branch is empty. Okay, there's nothing wrong with it. It is just less efficient. All right, moving on to a while loop. Okay, so you have to change your perspective a little bit when it comes to translating your C code into assembly or flattening the C code. This is the structure code, which means your block 1 can have 0 or any number of statements in it. Okay. And I did say 0 because sometimes the side effect of the condition is all you want to do. Okay, so I can give you a few examples later. Okay, if you're doing a string compare, you can have auto increment of the index or the pointers in C already, so you don't need a body. The body doesn't have to do a single thing because everything that needs to be done are done by side effects in the condition itself. But it's okay. Okay, the body can be empty, because it translates into something like this. Okay, it just translates into, this is the flattened version of a while loop. Okay, every time you see a goto, that involves a label that is defined earlier than the goto itself, you're looking at a loop. That's how you analyze the code and figure out, okay, we're dealing with a loop here. And then every time you're dealing with a loop, the next question is, how do we get out of the loop? What is the condition to get out of a loop? So with a pre-checking loop, the checking to get out of the loop, which is the telltale sign of the exit logic, is you have a goto that is right after the loop back to the earlier point. So whatever condition is here is your exit condition. So are we good so far with this? Yes? Okay. Does everybody understand why this go to L1 is mandatory? You cannot not have this one. Okay, because that's the only thing that turn this into a loop to go back to the beginning. Post-checking loops are simpler. Okay, you just have a label that marks where you want to go back to in case the condition to continue is true, and then you have a block of statements, possibly 0. Okay. And then you have a conditional branch, over here that says, if the continuation condition is true, we go back to L1. So this one does not invert the condition, whereas the other one does invert the condition. Because the other one is looking for the reason to get out of the loop. So are we okay with section 3? Okay. So after section 3, we move on to section 4. Section 4 basically says, what if C, all these condition C here, is just a placeholder. In other words, C really is not the condition that we are trying to understand or parse. C is just a placeholder for a possibly really complex condition. Are we good so far? So what if C is a complex instruction? How do we reduce those complex expressions to something that's simpler? So we'll deal with negation first. If the original statement that we need to deal with looks like this, now this is after the flattening, of course. So after the flattening, if we see something like this, where we have a condition, and the condition, the last thing that the condition needs to do is a negation, and then if the negation C, which itself can be complex, go to L1, what do we do with this? Well, we can translate it into something like this. Okay, we basically just say, okay, get rid of the negation. If the condition C is true, we go to L2. L2 is a new label introduced so that we can label the continuation point. Is that okay? What if C is false? Well, if C is false, we are not going to L2. And we're going to go to L1 in that case. Then somebody's going to ask, why don't we say else go to L1? Because the use of else is introducing structure again. We do not want structure. Yep.
How come there's no L1 in that statement?
Because L1 is just a placeholder of what the original statement is going. So it's just a placeholder. It's like if the original statement has the format of if negation of some condition go to some label, then what do we do about it? Well, we still go to that particular label, but only if we do not go to L2, which is a continuation label. So L2 is introduced in the translation process or the transformation process, but L1 is in the original form, and we just preserve L1 as it is. All right? So negation is simple, but we try to avoid negation as much as possible because there are other ways to get rid of negation. I'll show you guys what we can do in just a little bit. The second one, 4.2, is about or. In other words, if the original expression is some kind of conjunction, okay, C itself can be complex, D itself can be complex, okay, but the last operation of the condition is a logical or, then what do we do? Well, that translates to the following two conditional statements. We basically say if C is true by itself, let's go to L1. Because this is a disjunction, if one condition is true, the whole disjunction is true already. So we don't need to evaluate D if C is already true. Does that make sense? So this approach is also called the lazy evaluation of conditions. And more technically, it is called the short-circuited method of evaluating Boolean expressions. That is true for almost every modern programming language. So for every single modern programming language, when it comes to or, and, it is always evaluated from left to right. In the case of or, if the first condition is true, it doesn't bother to evaluate the second condition. In the case of and, if the first condition is false, then it doesn't bother to evaluate the second condition. So is that kind of discussed in CISP 300 or 360? I think we talk about it in 300, but what about the rest of the class? Was the concept discussed? Okay, because that is important. Some algorithms or the way they express some algorithms actually rely on lazy evaluation for the algorithm to behave correctly. Okay, so what if C is not true? Well, if C is not true, we are not going to go to L1 in the highlighted statement. We just kind of fall through to the second conditional statement. So now we have a second chance and say, okay, let's find out whether D is true. If D is true, then we'll go ahead and go to L1. But if both C and D are false, then we just fall through to whatever is after this block of statements. So it behaves exactly the same way as the original. So now we have 4.3, which is conjunction, which means if the overall or the last operation of an expression is conjunction. Now remember, C can be complex, D can also be complex, but I don't really care about C or D at this point. I just need to know that the last operation of this Boolean expression is AND. That translates to something like this. If I know C is false already, let's just continue. let's not even bother with condition D, which jives with what I just said earlier, right? Because conjunction is also using the lazy evaluation method, which means if I know the left-hand side of a conjunction is false, the conjunction is guaranteed false to begin with. Why would I want to bother with the right-hand side? So this is what makes it possible. On the other hand, what if C is true? If C is true, not C is going to be false, and if not C is false, we're not going to go to L2, not just yet, okay? Because in that case, we'll fall through to the second conditional statement, which now checks whether D is true or not. But by the time we get here, we already know that C is true. So if D is also true, then we have met the requirement of having both C and D being true. Then we can go to L1. Yes?
Won't we have to break that down again because now there's a not there?
Yes. So you recursive apply these techniques until you cannot apply any one of these techniques anymore. So this is all recursive. You break something down, and in the process of breaking it down, you might introduce something that you need to do something about. Okay. And then L2 is defined here as a continuation label, which basically means if C is false to begin with, let's just jump over here and continue execution because the whole condition is going to be false. All right. So do we have any questions about section 4? Which has to do with reducing complex Boolean expressions to something that's simpler, but it comes at a price. Okay, the price that we are paying is making the control statements or the conditional statements more complex. There are more conditional statements, more go-tos and more labels, but the effect is we are reducing the complexity of the Boolean expressions. So do we have any questions about this section 4? No questions about section 4? All right, so now we move on to section 5, which has to do with comparison. Now this is really important. It really ties into the processor architecture itself. In other words, depending on the processor architecture, we may or may not need to do this type of transformation. With text toy processor, the only thing we can do is JCI, JSI, JOI, JLI, and JZI. Okay? In other words, we can say if C is true, go to a particular label. If Z is true, go to a particular label. If L is true, we go to a particular label. C is the same thing as borrow after a compare. So that is applicable when the minuend is less than the subtrahend interpreted unsigned. So we can confirm, okay, whether the minuend is less than the subtrahend unsigned using the C flag, and if that is the case, we can go somewhere else. The Z flag checks for equality after a compare. It is sign insensitive, okay, because whether it's signed or not, the same is the same. So the Z flag can be used to confirm whether two values are identical, and if so, we can branch. And then the L flag is kind of like the C flag, except it applies to signed interpretation. But once again, it can only confirm whether the minuend is less than the subtrahend. So that means we want to translate all of the comparison operators to just using less than or equal to. Okay, because the instruction set only supports the confirmation of less than or equal to. So now we look at every single comparison operators that is under the sun, and we say, well, what do we do with this? Assuming x and y are registers already. If we need to confirm whether x is less than y, we can deal with that. So there's no need to reduce this to anything else. If we're looking for x is greater than y, well, we can just reverse y and x. So now it becomes less than again. Not a big problem, easy to deal with. If we want to confirm x is less than or equal to y, then we just spell out x is less than y or x equals to y. Because each one we can confirm individually. If we need to confirm x is greater than or equal to y, then we just kind of flip the order, okay? If we need to confirm x does equal to y, we can just leave it as is because we can check for equality. And if we need to check for x does not equal to y, then we use a negation and say, it is not the case that x equals to y. Now, all of these logical operators were introduced at the beginning of this class. So if you need to have a little map of what this symbol represent or what this symbol represents, you might want to go back to one of the first few modules that we talked about in this class. But in terms of concept, do we have any questions about how we can translate comparison operators so that we only use the ones that are supported by the architecture? Are we all good here? Yes? Okay, excellent. So now we go to general comparison, okay? So the format is like this, okay? If we know that X is a register and Y is a register, what is that R doing here? R is a relation, okay? If you have taken cisp 440, you know what a relation is. If not, you will know, once when you go take cisp 440. But in this class, we don't talk about relation, by itself. Relation is really just less than or equal to, greater than or equal to, and not equal to. So basically, R is a comparison operator. Is that okay? So if this is what we see in the C code, after all the flattening and whatnot, how do we translate this into assembly code? It translates to here. So we first start with a compare, assuming X and Y are registers already. And then whatever R is here is becoming this R over here. Wait, but in the assembler, we are not supposed to use less than as a part of J less than I, right? We cannot have an equal and say J equal I. So what do we mean by, this R goes here? Well, if it's less than, it becomes either a C or an L, depending on whether X and Y are signed or not. If it is equal to, it becomes a Z. Is that okay?
L would be the signed comparison. L is the
L is for signed less than, and then C is for unsigned less than. Now, how do we know, whether it's signed or not, and which flag we pay attention to, depending on whether it's signed or not? That was discussed in the module. I think it's called binary comparison, and it was a long time ago, but still in this class. So I'm counting on you to kind of either, having retained that knowledge, or going back to review that so that you understand, which one to use under what condition. So are we good so far with this discussion here? Yes? Okay. So now we are almost done. So section 6 talks about naming convention, and this is just my recommendation because in the course of translating C code into assembly code, depending on the complexity of the C code, you might need to use a lot of labels. Okay, it would not be uncommon that you have to use like 4 or 5 labels even in a very simple piece of code. So now the question is, how do you come up with new label names? Okay, that becomes the question. One way to do it is to simply use a sequence number, or use numbers in a sequence. So you start with label L1, and then the next label becomes label L2, L3, L4, L5, and so on. The beauty of this approach is all you need is to count. Okay, the problem of this is look at L11, and you go like, well, but what is the meaning of L11? You have to look at the context of L11. How do I get to L11? Where is the position of L11 to figure out what L11 is? It also becomes very easy to have a typo. Okay, because hey, instead of typing L11, what if I mistype it as L10? Now, in order for L11 to exist, L10 also has to exist, right? So now if you branch to L10 instead of L11, your program is wrong, but the assembler cannot catch it because L10 does exist. You're just branching to the wrong place. So that is the downfall of having just using a sequential number to label, to come up with new label names. Okay, it's great if you're a compiler because a compiler doesn't get confused when there are like 100 labels, they all started with L with just a different number at the end. But from human perspective, it is actually much harder for us to just look at a label name that is L and then the number to try to figure out what that means. Okay, so I would not recommend that particular method. The other section, talks about, section 6.4 particularly talks about a nested construct method where the label names are nested. Okay, so instead of just reading this out, I'm just going to give you an example. Okay, so this example that I'm going to give you would also explain the process of translating C code into assembly code in a step-by-step manner. So I'm going to write this code first. Okay, we'll say a equals to 20, while a do the following. And what we're going to do here is we will auto increment. So we check first, or auto increment first. Yeah, we'll auto increment first. So we'll do a b plus equal to 13, and then we'll say if b is greater than or equal to 40, let's make it different. Let's make it 35. Then we do the following. And this is actually, how I write code in C, C++, JavaScript, or whatnot. Whenever I use a conditional statement or loop or any type of control structure, I automatically use curly braces. Even if there's only one thing to specify, I still use curly braces. And why do you think that is the case? So in case I want to add something later, instead of just having one statement, I want to have two statements. I don't have to think about that anymore. I just add additional statements because the curly braces are already in place. Okay. Now the other thing is if you start with the open curly brace and immediately close with a closed curly brace and then just go back to reinsert something, it seems like you're using extra keystrokes, to have to go back and reindent or whatever, right? But it saves me all the hassle of later on trying to match close parentheses because they're automatically matched already. So it does give me, all of those advantages. Yep.
It cleans up the code too, so it makes it easier to find. Makes easier to find nested statements.
Yes. Well, if I do it this way consistently, I would never end up with a missing close, curly brace.
Most compilers also tell you which curly brace belongs to which too.
Right. Most GUIs, most graphical user interface, or IDEs in this case, integrated development environment would also do that. I use VI. VI does have matches like that, but even without any tool to help me match the parentheses and the braces, I don't have to worry because it's automatically matched. Okay, so in here I want to do a b minus equal to 35, and auto decrement A. So let's see, would that work? Yeah, I think that would work. Okay, so this is the code that I want to translate into assembly. The meaning of this code, I'm not going to talk about it too much, just because it's known as a frequency divider. Okay, so you have a tick frequency that is much higher than what you want, and this is what we can do, to quote unquote divide a base frequency into a kind of a lower frequency. But we're not going to get into this too much. We'll just go ahead and say this is what we want to translate. So this is the original C code. We'll call this version 1. Okay, so this is version 1 of the code. So let's go ahead and try to translate this. So the way I like to translate C code is I would do it from the outside in. In other words, I look at I only do one control structure at a time. I would not try to attempt to translate multiple control structures at the same time. And the way I work on this is always from the outside in. So I'm going to take care of the while loop first. And once I take care of the while loop, then I go in and take care of the conditional statement. Okay. So now what I do is I just comment out the things that I'm going to replace. And with a while, I know I need a label to mark this spot so I can come back to this later on. So this while loop has a name of while 1 because it is at the root level and it's the first loop. Somebody's going to say, but this is the only loop, you don't have to count. But if I always name it as while 1, then if I have a second loop, I can name that while 2. If I have a third loop at the same level, I can name that while 3 and so on. So I don't have to go back and change the first one to while 1 afterwards. So I always like to kind of label or number the construct. So this is while 1, and this is the beginning of that particular loop. So I use a begin to label that. And what I usually do is I go straight to the bottom of this loop and say, yep, we have to go back to that. Okay? So I don't forget. In other words, when I do the translation, I do it by structure and not by line number. Then I can now go back and say, okay, now that we have an infinite loop, what are we going to do to get out of this loop? What do you think? When A is not A, right? Not A would be a good reason to get out of this loop. So we say if not A, go to while 1 end. And then I immediately define where that is supposed to be. While 1 end should be defined over there. Is that making any sense? So I take care of the infinite loop first, and then I take care of the reason to get out of the loop. We good? Okay. All right. So now this is taken care of. We'll call this version 2. So I take version 2, Control C, and I now work on version 3. So I'm going to take care of the conditional statement this time. Not this one, this one. Why not this one? Well, this one is already the flattened while structure. I'm kind of done with this one. Yeah, I know I have a negation to deal with, but I'll deal with that later. So I want to deal with this conditional statement now. Okay, same thing. Okay, we comment out everything that is structured about this code that I'm translating, and then replace that with the actual code that I need, the flattened code. So in this case, the flattened code is going to say if not b is greater than or equal to 35, go to while 1 underscore if 1 end. This is what I mean when I say I name my labels in a structured way. So I'll explain that in just a moment. Let me just write this down first. This is while 1 underscore if 1 end. This is the definition of the label. So when I say it's structured, it means when I look at a label, I know exactly structurally where to find it in the original C code. So like in this case, okay, while 1 underscore if 1 end. I know this is inside the while 1 loop. Inside the while 1 loop, there's a condition. This is the first conditional statement, and we are looking at the end label of that conditional statement. Is that okay? So if you take this and say we are in the first while loop and the first conditional statement, and you go back to the original code, you can easily find what construct I'm talking about. So that makes it easier to link the translated or the flattened code to the original code, because structurally I still preserve that information by using these label names. Is that okay? And if somebody has to complain and say, but this is a lot of typing, this label is kind of long, okay? It's better to spend the time to type the label than having to fix logical problems later on if I use generic label names like L0, L1, L2. Yep.
Doesn't this still have the same problem you mentioned earlier, where if you make a typo on a number, you're going to end up on the wrong?
Yeah, yep, it would. Yep. But are you going to have a typo, of, I mean, I understand the 1, 2, and 3 you can still have a typo with that, but it is much less confusing when you have like 20 L something labels, because these are all fairly distinct, when it comes to what it looks like. Mm-hmm.
Is there a difference on why you use that colon and semicolon at the bottom?
The definition uses a colon, and then the reference uses this semicolon here. Just is necessary because go to is a statement. Okay. So are we good so far with version 3 of this code? Okay. So after version 3 of this code, which is already flattened, I can now look into the conditions and say, okay, do we have any type of complex conditions that I need to reduce? So this is version 4. Yep, looks like we got a negation of A here. I'll deal with this later, okay? Because there's an easy way to check whether something is 0 or not, okay? So if you see something like this, the negation of a particular value, you can always just kind of change that to say, we just want to confirm it is 0. It means exactly the same thing. Okay, is that okay? I mean, does everybody understand this is what you can do in C and C++? Okay. And then we look at this one here and go like, that is a really long way of spelling out B is just less than 35, right? So this is what you can also do, in some cases with negation. So instead of using section 4, the section 4 method to get rid of a negation, you can just transform the comparison operator itself to simplify things and get rid of negation at the same time. Okay? So, and do we have anything else that is kind of complex? Yeah, I think we're good. This is version 4. Now we will work with version 5. So version 5 is going to look at this and go like, I don't think we can translate this I don't think we can flatten this any further. This is basically as flat as it can possibly be. There's no structure in this code anymore. Okay? Now, up to this point, can version 4 compile using a C compiler? Okay, this is version 4. I mean, I haven't done any changes yet, but in case you want to confirm, this is version 4. Do you think it will compile? Why would it not compile? It's missing the keywords. It doesn't need the keywords. So a C compiler can recognize a label definition and go to is a valid C statement as well.
Can you give semicolons at the end of some of your statements?
Some of my statements, where?
Like B plus equals 13.
Okay, fine. Yeah, that's a good point. Okay, we need that. Yep.
So since it understands go-tos, it also understands labels?
Yeah.
Oh.
Yeah, C compilers can handle those. They're strongly discouraged in CISP 360, 400, and 430, and all the future classes that you ever take. But in this class, this is what we need.
Why would they be discouraged is my question.
Because it leads to spaghetti code.
But this is just conversion.
This is a very structured and mechanical conversion, which means the code itself is actually still structured from the perspective of how one construct is nested within the other one, but the way it is expressed is not structured anymore, because we are not using curly braces, we are not using block statements anymore. Yep.
A and B don't have to, A doesn't have a type, and you didn't, not initialize B, but you didn't create a variable.
We did not declare A and B. So we are assuming that A and B are registers, so they do not need to be pre-declared. I do need to indicate whether they are signed or not, okay? Because when we have something that is a comparison other than the equal to, the sign is important. So we can assume, okay, let's assume A and B are unsigned, okay? So we can make that assumption, okay? So other than those things, this is still C code. In other words, okay, what I want to point out is, if this code compiles, the new code, okay, we have that missing semicolon, but if this is a portion of another piece of code inside the function definition and it compiled before, then the version that we have at this point would also compile. Is that okay? So given the context of the original code does compile, given the same context, this code will still compile. Is that okay? So if the original code is inside a C function, A and B are declared, blah, 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 it would compile, but this will still compile. And it will still do the same thing. So logically, the two pieces of code from version 1 all the way to version 5, at this point, they are still functionally equivalent, which means you can use your C compiler and you can use a C debugger, you can use code blocks to debug the code and make sure that the behavior of the code is preserved up to this point, because there's no assembly code whatsoever up to this point. Is that okay? So the flattening process, as tedious as it is, okay, and as easy as it is to introduce errors and whatnot, you can use a C compiler to do all of this work and debug your program up to this point. Are we good? So at this point, you cannot flatten the code any further because, everything is boiled down to comparison, involving registers. So now we can start to compile this or actually translate this into assembly instructions. So version 5 is the one that has actual assembly instructions. So now we can comment out the actual C code and replace it with the equivalent assembly code. Okay. Label definitions are fine. We do not need to do a single thing about label definitions. So this one, okay, which is checking whether A is 0 or not, I can translate this into AND AA, and then the JCI to the label that is stated here. And you go like, but the original code doesn't call for AND, so why am I using AND? Besides, I'm using AND AA, which doesn't do a single thing, right? Because if A is the bitwise AND of A and itself, okay, it means I'm not changing A in any way. But that operation did go through the ALU. And anything that goes through the ALU other than increment or decrement will change or affect two flags for sure. The Z flag is always affected, and then the sign flag is also affected. So what this is going to do is if A is in fact 0, and AA will set the Z flag. If A is non-zero, and AA will clear the Z flag. Is that okay? Now, if you are not really sure about that, then I strongly encourage you to write this code, okay? Not the entire thing, just AND AA and then a halt instruction right after that, and then inject a particular value into A, either 0 or non-zero, and then go through the single step process, the control T process, and then just freeze the frame when the AND AA is going to execute and figure out how things operate, right at that moment. Okay, because that is how you study for this class, is to look into the execution of instructions, by looking at the architecture, find out how the multiplexers, demultiplexers, the enables, the selects, how they work, as a whole, in order to understand why this works. Is that okay? Does everybody understand what I am recommending? Okay. Now, if you look at this code and you already know how it works, great. Okay, that's good. But if you look at this code and do not understand how it works, then I recommend you to do what I just said. Okay, B plus equal to 13. Okay, the first and most people would say is oh, we can just do an add. B is the destination, and we'll just specify 13 here. That does not work. Now, how do we know that does not work? Okay, you don't even need the assembler to tell you that it does not work. If you refer to the opcode table, what are the two operands that we can expect with the add instruction? Two registers. X is a register and Y is a register. 13 is not a register. Okay, so we cannot do it this way. So this is the reason, okay, this right here is the reason why we spent the first half of the semester talking about transistors, gates, the adder, and then the flip-flops and the latches and so on and so forth. Because if I just introduce the syntax of the assembly instruction, then someone's going to say, oh, we will just add the two things and update the first thing. They will naturally think that we can just put a 13 as a constant as the second thing. But that is not the case. Why is it not the case? Because when you refer back to the assembly, the opcode table, okay, now I need to go find where I put it. Exactly, there's no way to express the 13, but I want to point out here why there's no way to express the 13. And by the way, that field trip to Lake Observatory was great. I left my house at 7:30 to get to here, and then I got home at 2 a.m. the next day. But it was great. I would do it again if I could. Let's see, go to processor, and then we go to opcode table. Now the opcode table is still just a document to describe the opcodes, but it will give you a sense of why it cannot be done. So when you look at add, it says add expects two things, okay? X is a register, Y is a register, and this is how we encode which register as a part of the opcode. How do you specify 13? Not possible. Is that okay? Yep.
Well, we could set one of the registers to 13. And
Exactly. You can use a temporary register out of the 4 and say, I'm going to put 13 into this register and then use that register as if it is 13. Yes, so that is what we need to do. But what I want to do is to point out why we cannot say add and then a register and then 13 as the second operand. Now, because if you take this class from other colleges, okay, they just start talking about the opcodes and the instructions and whatnot, then there's no reason in your mind, okay, to say why can't we specify a constant instead of a register, because they don't talk about this. Because you cannot. Okay, now, yep. Now, can we, make a new instruction so that we can do an add I, add immediate? Now, that's a different question, okay? That question is actually kind of complex and it will take a long time to explain one way or the other. Question? Nope, okay. All right, so we cannot do this, but we can certainly find a register that we have not used up to this point. I think C and D are both free, okay? So we'll use register C for this purpose. And then we just say LDIC with 13. So now we're adding 13 to B, but in the process, we're clobbering register C. Okay, so that's okay. So now we look at this one here and say, how do we compare B to 35? And if B is less than 35, we go to that particular label. Same thing. Most people would say, well, can we do this? No, for the same reason, okay? So if we cannot do this, can we use register C again? Yeah, we can. I mean, this time we have to do LDI C with 35, then we compare. Okay. After we compare, this is looking for less than, and I think I said A and B are both unsigned, so JCI is what we need to go to while one underscore if one end. So that takes care of that. So by the time we get here, we want to subtract 35 from B. Now, is that going to turn 35 into something that is less than 0? Do we have to worry about that? Nope, because we won't be here unless B is at least 35. Okay, so we know for sure that B cannot go negative, so having B being unsigned is fine. So this is done by just doing a subtract B, C. Okay. Whoa, Tech, hold on a second here. How do we know that C has 35 in it? Because we could not get here until we get past that, right? So C still has a constant of 35. Okay. But this is optimization. In your test, okay, you don't have to optimize. So if you don't know for sure and you don't want to spend the time to do all the analyzing, you can just reload it, okay? It's not considered wrong. In this class, I'm not that concerned about efficiency. All right, so that is that. What about decrementing A? We just want to decrease A by 1. We actually have decrement, which is nice to have. So you don't have to use another register to store 1 and then do the subtraction. All right. Oh, we have a goto here. We have to translate this goto to a jump. or JMPI, while one begin. And now we're done. That's the translation process. So after the translation process, how do you know this code is still going to do exactly the same thing as the original C code?
Put it in the
You have to put it into the assembler, okay? Assemble the program, put it into RAM, run the program. But how do you know the behavior of this code is still the same as the original C code?
run them side by side.
You can run them side by side, okay? Yep, go ahead.
Well, if we go step by step,
Mm-hmm.
we can do this. This one's going to be an easy step by step because register B is 0, so it's like half the code is skipped.
So it does get a little bit difficult. The assembly code itself has a trace. Okay, we can use the trace analyzer to help us fully understand how many times we got through a particular label and so on. So that's the easy part. The difficult part is actually the original C code. In other words, in the original C code, you can kind of count how many times we get past this, and when we get past this, what is the value of B. So you can do a watch expression. Okay, you set up a breakpoint right here, and then every time you stop, you do a watch expression, and you kind of jot down the value of A and B at a time, and then you basically go to the same place in the assembly code, and then in the trace analyzer, you say, okay, at this location, what are the values of A and B at that point? So you have to double check and make sure that they get updated, at the same time, and they have the same value. Okay, so it does get a little bit complex, and the complex side is coming from the C side because the C debugger does not naturally have a logging ability. So you kind of have to do some of the logging yourself. Now you can insert some C out or printf, if you want to, just so that you have some references of, okay, every time we get past this code, this is the value of B and this is the value of A and so on. But you do need to do something like that. All right, so are we good with this whole process? Okay, so I'm going to open up the lab for this portion. So let's see which. Yeah, I normally have time in the morning to open up lab stuff, but not this morning. This morning I had an hour-long meeting, so I didn't have time to do it. All right. So it's absolute value, blah, 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 blah. Okay. And today is the 5th, right? So plus 7, that will make it the 12th. So we have November 12th, which is not a holiday. I think the 11th is. Yep, but not the 12th. Yeah, so make it due at 9 a.m. Canvas is very specific about the format of the time. For instance, my natural tendency is to use military time, like 0900, which is an easy way to do it. Nope, Canvas wants to know AM and PM. If I use the wrong format, it doesn't like it. All right, so the lab is released. And we got 15 minutes to talk about subroutines, calling and returning, which is really cool. So that's what we'll do. Okay, so get back to the notes here. I just want to show you where we are at this point. So we are basically done with compiling C control structure, and we are now moving on to calling and returning from subroutines. This is the new topic. Oh, by the way, on Thursday, we're going to have a practice test, so that next Thursday we'll have exam 2. And yes, I will have your exam 1 graded by that time. I did a lot of grading over the weekend, but still not enough to get everything done. All right, so this is calling and returning from subroutines. So I want you to kind of focus on the C code first, okay? So you look at this C code, you go like, what is the point? right? This program doesn't do a single thing. But it does illustrate one thing, okay? So let's try to follow the execution of this program. Just mentally, we don't need a debugger to follow this, right? So we start with a call to function f, okay? So we go to function f, and function f said, I got nothing to do. By the time we get to the close curly brace of function f, we need to return. The question is, where are we returning to? We go to the second line, right? We don't want to go back to the first line, because if we go back to the first line, we'll be calling f again from the first call. So now you have to ask the question in your head and go like, but how does it know that at the end of the first call to function f, it knows that we have to go back to the second call of f? So keep that in your mind first. So let's say we magically knows how to do it. So in the second call of f, okay, same thing happens. We go to f, says I have nothing to do. When we get to the end of f, it says, okay, we need to go back to the caller to continue execution. But this time magically, it also knows that we're supposed to go to the return 0. How does it know that, right? That's just mind-boggling. Except for people who took cisp310 from me. Those people going like, yeah, you talked about this a year ago, okay? There's nothing exciting about this class. So the question is why? How does the function know where to go back to? It leaves behind a little breadcrumb, okay? So before we continue execution in f, in each call, it remembers something and say, hey, by the way, we need to get back to this location. It saves that information before continuing execution in f. Now, at the end of f, it knows where to find the information. It's like, okay, I'm at the end of the execution of a subroutine. Where am I supposed to go back to? It just looks up something that it has stored earlier and go like, okay, according to this, I'm supposed to continue execution over here. Or after the second invocation, it knows that it has to continue execution over here. So there's something hidden, there's something done behind the scene that we normally do not see, but in this class, we have to talk about it. Okay? So now the question is, what is that construct called? And section 3 talks a little bit about what a stack is. So the one thing about the stack that you really just have to remember is it is a last in, first out container. Okay? Now, if you have a problem remembering what is last in, first out, or what is a stack, think about the U-Haul truck. Okay? So it's a U-Haul truck, and you're trying to load something in to move from one city to another. Okay? And to make sure that you do not lose your map, you say, I'm going to take my map and put it in the truck just so that I don't lose it. And that's the first thing that you did. So you put that map on that shelf, the granny shelf on the U-Haul truck, and say, okay, this way I won't forget to bring the map to the new location. Then you proceed to load up the truck, right? And then you load up the last bicycle, and then you have to slam the tailgate, because otherwise things will start falling out, right? Then you go to the driver's seat and say, okay, now we are ready for the trip. Except you don't know where you're supposed to go. Then you go like, yes, but I accounted for this. I put the map in the truck to begin with. So I know the map is in the truck. But where is it in the truck? And how do you get to that? You have to unload everything first. That is last in, first out. The very first item that you put onto the truck is the last thing that you can retrieve. Now that last bicycle that you push onto the truck before you slam the tailgate, guess what? That is the first thing that will fall out of the truck when you open the tailgate. Last in, first out. So is that okay? Do you guys know what is last in, first out? Okay. So that's kind of what we need to know about a stack. So the way we utilize a stack, okay, can be done using some C code here. I'm just using some C code to illustrate what we do with a stack or how we maintain the state of a stack. So if you don't like pound define because you're not exposed to pound define, you can kind of say const unsigned stack size 30 equals 32. Okay, it's kind of the same thing. In this context, it can be seen as the same thing. Then we have an array called stack. It has stack size, which means it's an array of 32 basically unsigned bytes. And then we have a stack pointer, which is a pointer to unsigned 8-bit integers. So those are the definitions. So the way we do this is when we want to push something on the stack, in other words, when we want to store something on the stack, this is what we do in that operation. The stack pointer always points to the last thing that we push on the stack, the very last thing that we store on the stack. So this is what we do to store something new on the stack. You see that we are decrementing the stack pointer because the stack, unlike most things that grow from low location to high location, the stack goes in the opposite direction. When the stack is empty, the stack pointer is as high as it possibly can be. When the stack is full, which means it has no capacity to store anything else, the stack pointer is as low in the array as it possibly can. Now, why do we do it in a strange way? Why are we reversing, from the normal way of counting? There's a reason, and I'll explain that later. But this is how we do what we do when we want to store x on the stack. X can be a complex expression for all we know. We don't care. So we reserve the space on the stack first. We basically say, okay, let's reserve one more byte on the stack. Because remember, SP, or the stack pointer, points to the last thing that we have stored on the stack. So we don't want to overwrite that location. We have to move the stack pointer first and say, okay, that location is already in use. This is the next available location. Once we are pointing at the next available location, then we can say, okay, now we can store x to whatever SP points to. This is just plain C code. This is not assembly. This is just plain C code here. So do we have any questions about these two lines of C code? The first one to reserve the space, the second one to store something into that space. What if you want to retrieve something from the stack? Exactly the opposite. Now this is opposite in two different ways. You can see that SP minus minus is the opposite of SP plus plus. You can also see how the assignment is exactly the opposite of each other. You can also see how the ordering is also opposite to each other. So when you're ready to retrieve something from the stack, the first thing you do is to say, oh, the stack pointer points to the very last thing that I push on the stack. Let's retrieve that first. Okay? So the first statement in C retrieves whatever the stack pointer is pointing to, and you put it into something that's temporary. Okay? So typically in assembly language programming, you put it into a register. But that location is not useful anymore because we have just retrieved the content at that location. So now you have to say, that location is not of use to me anymore. How do you say that? You increment the stack pointer. So what you can do in your mind is to imagine the stack itself is like a notebook. Okay, many of you still have a notebook in front of you. Okay, so I have one too. So let me use my notebook. Okay, as a prop. So you have a typical notebook. Okay, so let's say page 1 or the first page is the low memory location, and the last page is the highest possible location. So what we are saying is the stack would use the last page first, and then as you use more and more location, you're working your way to the first page. Now that's a really awkward way of doing things, but that works out really well when for what we use the stack for, and we'll see why that is the case. Are we good so far? So what is the stack pointer then? Okay, let me see if I can find something to help illustrate that. I don't have exactly what I want, but I have something that works equally well. The stack pointer is a bookmark. That's basically what it is. So the bookmark says, okay, whatever page the bookmark is on is the last page that is still in use of my stack. Is that okay? So in this case, this back cover here is the page that I'm on. This is the one that is in use. So when you're pushing or when you're trying to store something on the stack, what you're doing is you're saying oh, this page is already in use. Let me move my bookmark to the page before, which is not used at this point. So you're moving a bookmark first. Once your bookmark is on the page that can be reused, then you scribble on it. Is that okay? So that's how you use up multiple pages. Okay, you keep using more and more locations on the stack, and your bookmark is always on the last one that is still in use. Is that okay? So now you go like, okay, we are at the end of the execution of a subroutine, and the where we need to go back to is stored in the stack. Okay, and it's the last thing that I store on the stack. So what you do is you flip open the notebook, go to where the bookmark is, look up that page, look at the content of that page, and it will tell you where to go back to. It will tell you which location you need to go back to continue execution after the subroutine is done. So you look at that and go like, oh, I need to go back to location 25, okay? But once you have used that location, because now you know where to go back to, this page is no longer useful. It can be reused. So what you do, you don't tear the page out. Instead, you move the bookmark onto the next page. So now that page is once again available. Is that okay? Is this analogy working? Okay. It's not going to help people who are just watching the video. Well, the description may help, but it's not the same. All right. So when you look at these two operations, do you think we can do these in assembly code? And if so, what instruction would be useful for that? So if you assume the stack pointer is one of the 4 registers, how do we do SP minus minus? Decrement whatever register, right? And how do we do this part here? Star SP equals to X, assuming X is also a register. Which instruction do we use? Store, very good. Yep. Okay, so we use a store instruction, and the register that is being used as SP would be in the parentheses, and then the other register, which is the first one, is going to be X. Okay. Well, this is exactly the opposite, right? We use a load instruction, and then we use increment to increment the register. Are we doing okay so far? So these are fairly easy to implement using assembly code. So now how do we initialize the stack pointer? That's the next question. So in the C code that I give you, this is how we initialize the stack pointer. So let me zoom back into how we declare these constants. This is how we declare stack. Okay, so given this is how we define the stack, okay, let me see if this will work. I know the font size is a lot smaller, but I want to show both this part here and also how we initialize the stack pointer. Somebody is going to look at this and point out and say, but the stack pointer is now pointing to something that is not a part of the stack, because this is pointing to the byte that is right after the stack itself. Okay? Is that okay? Is everybody comfortable with pointer arithmetics? You can add constants to a stack pointer, to a pointer. Is that okay? But this is pointing past that last page, which is actually fine, because if we want to store something on the stack, what is the first thing that we do? Are we going to store first, or are we decrementing the stack pointer first? We're decrementing the stack pointer first, which means it is okay to initialize the stack pointer to point past the last byte of the stack, because the first thing we do is we decrement the stack pointer first. So this is actually perfectly okay. Are we doing okay so far? Okay. All right. So we are running out of time today for the lecture. We are going to use Thursday for our practice exam for exam 2, which will cover everything, including compiling. Okay, but it would exclude discussion of the stack. So that would be our clean break. This module is not in the test, but everything before this is in the test. I cannot say whether it's comprehensive or not, because you will still need to remember binary comparison, what the flags are for, and so on and so forth. So I cannot say that it is not comprehensive, because you still need that knowledge in order to take exam 2. But I will not specifically ask you things like things that are specifically before the first exam, so they will not. Okay, for instance, I'm not going to ask you, what is the range of value as minuend when this is the subtrahend to make it overflow. I will not ask those questions. But do you still need to understand what is the L flag and the overflow flag and the sign flag and the Z flag and the carry flag? Yes. Okay? All right, so we're going to head out to the lab, and I'm going to stop the recorder.